ठीक है भाई. Okay. Hello. Dear participants, we'll start 11:30. Our today's session will start from 11:30. Although I dropped a message and mail to all participants, but still I think some of you have still confusion on this timing. From today onward till the end of our FDP, our timing is from 11:30 on, right? So please take care of that. And we start sharp 11:30. Our resource person will join around 11:20. Okay. Please stay with us. I am here only. I will keep it logging so that no technical problem will be occur.
Are focusing more on the impedance spectroscopy, and so which is very useful for those who join this talk, so that we can share and discuss any new study or any problem related to impedance spectroscopy. So without further ado, let me share my slide. So I think we can see the slide, right?
Right, it's visible.
All right, okay. So today I'm going to share about a method based on impedance spectroscopy to determine transport properties of polymer electrolyte, right? So, okay. So basically, we know that the polymer electrolyte is are an ionic conductor that many use in electrochemical applications such as a battery, fuel cell, supercapacitor, DSSC, electronic device, and electrochemical sensor. And the polymer electrolyte nowadays become a hot topic around the world, because nowadays in line with the 7 SGD towards the clean energy. So we are focusing more on using the environmental friendly of what we call energy devices, which is focused on battery and also the solar cell. And polymer electrolyte also contribute for this kind of electrochemical devices. So in order to obtain a good the good performance of electrochemical devices, basically we have to choose the best polymer electrolyte, so that because the polymer electrolyte act as a medium for charge transport. So the best polymer electrolyte is very important, because it will contribute to the performance of electrochemical devices, especially in terms of their for example, if you use a solar cell, in terms of their efficiency, if you use in the batteries, in terms of their capacity. So much studies have been done to produce the best polymer electrolyte in terms of ionic conductivity, thermal mechanical, and electrochemical stability properties. And among all these properties, the focus is on their ionic conductivity. So basically, the ionic conductivity is given I try to use laser pointer. Okay, is described by sigma is equal to n mu and E. So n is the number density of charge carrier, mu is the mobility of charge carrier, and E is elementary charge. So this is a basic equation for the conductivity. And from this equation, we can see that n and mu, which is a number density of charge carrier, and also the mobility of charge carrier, are the two important parameters that control the conductivity of polymer electrolyte. If the conductivity of polymer electrolyte is high, it may due to the high number density of charge carrier, or mobility of charge carrier, or maybe both n and mu is higher, either one is higher and one is lower. So we do not know which one is the which parameter that contribute to the conductivity. So in order to obtain the high ionic conductivity, n and mu should be as high as possible. So we must so it is useful if we can determine n and mu quantitatively, so that we can modify or we can prepare a polymer electrolyte that can have a high ionic conductivity. So theoretically, basically, when we perform the impedance spectroscopy, we sandwich our polymer electrolyte between the two blocking electrode. So during the impedance measurement, the polymer electrolyte is sandwiched between two blocking electrode, which is we use a stainless steel electrode, and a small sinusoidal potential. Basically, we use a 10 millivolt. It's applied across the sample, and the current through the sample is measured, right? And from this, the impedance is obtained for each operating frequency. Basically, we apply from 10 Hz to 1 megahertz. And during this process, the anion and cation in the electrolyte will accumulate at the interface of electrode. We can see this is the polymer electrolyte that has a positive and anion and cation. It will accumulate at the electrode interface of the electrolyte and electrode during the impedance process. And this will form a Helmholtz double layer, or known as an electrical double layer at this interface. So this electrical double layer on both sides of electrode behave as a capacitor with capacitance of CE. We can see at this EDL will behave as a capacitance. We denote it as a CE. And the polymer electrolyte between the two electrodes now act as a capacitor with a geometrical capacitance C, because we have a one side of negative anion, one side of anion, one side of cation. So this electrolyte will form a geometric capacitance with and we do not it as a C, and also it has a buck resistance. Therefore, we can assign or we can equalize this situation with the equivalent circuit. So a polymer electrolyte sandwich by an specific parallel. You can see parallel with it connected in series with another two capacitors as a EDL layer. Here we can see we have a layer here C and a straight. So this Nyquist plot can represent by using the equivalent circuit of a resistor in parallel with a capacitance and in series with another capacitor. All right. Okay. So this is a theory, but okay. And based on the equation from this equivalent circuit, we can derive the real and negative imaginary of complex impedance, and the equation is given in on the slide. So we can see this is the equation for real impedance, and this is the equation for the imaginary impedance. And from here, we can also determine the value of resistance, capacitance, and EDL, electrical double layer capacitor. So basically, based on the equation of conductivity is equal to thickness divided by resistance per area multiplied by area. So we can determine R is equal to D divided by sigma A, which is the conductivity multiplied by A. And capacitance is equal to dielectric constant of a material multiplied by vacuum permittivity multiplied by the area, which is the electrolyte contact area, divided by the sample thickness. And for the EDL layer, the same as equation for the capacitor, but the thickness now is the thickness of at the EDL interface. But when we perform the impedance measurement using the polymer electrolyte in a real system, we will not get or we will not obtain a perfect semicircle and straight spike. We will have a depressed semicircle like this and a tilted spike as shown on your screen. Okay, and this graph or this plot can be assigned to a circuit consists of a resistor parallel with constant phase element and in series with another constant phase element. The constant phase element is an equivalent circuit component that model double layer behavior, which is it is imperfect capacitor, or we also known as a leaky capacitor. It is a not perfect capacitor, right? So if you can see here, the R and parallel in CPE will give represent the depressed semicircle here, and the CPE here will represent a tilted spike here. Okay, and this is the equation for the constant phase element. The real and negative imaginary of a complex impedance of a leaky capacitor is given as this one, this equation. So so if you can see here, K is a reciprocal of the capacitance, and pi p per 2 determine the angle or the inclination of the spike, and the value of P is varied from 0 to 1, depends on the inclination. And if you can see here, if the value of P is 0, it become a pure resistance because it will become a dot, one dot here. And if P is equal to 1, the spike will form a straight a vertical spike, so it will act as a pure capacitor. And if P is equal to 0.5, so this CPE will behave as a Waubach element, right? Okay, and we are based on this equivalent circuit, we derive the equation to determine to obtain the real and negative imaginary part of impedance, and this is the derivative equation for the real and negative imaginary of impedance. So this is a quite long equation. So you all can use this equation to fit the Nyquist plot obtained from the experimental. So we can use this equation to fit the Nyquist plot obtained from the experiment. So basically, according to the Bandara and Melander, so they say that the diffusion coefficient of the charge carrier in electrolyte is given by lambda squared divided by tau 2. Lambda squared here is the thickness of EDL layer, and tau 2 is the minimum, is the characteristic time constant corresponding to the minimum in imaginary impedance, which is at this point. If you can see here, this is the tilted spike. From the lower frequency, it increase and it will going down, and it increase back. So and then it will form a depressed semicircle. So the value of tau 2 is the reciprocal of the omega 2, which is at here at this point. So the frequency at this position, and if we can see here, the D is equal to the lambda squared. Lambda squared is the thickness of EDL, and the thickness of the EDL, the electrical double layer, is very, very, very small, and it's difficult for us to determine. Compared to the geometrical capacitance, we only use the thickness of the sample, so we don't have a problem to determine the thickness of the sample. But here we need to determine of thickness of the EDL, because we cannot determine the thickness of the EDL. We modify the equation, whereby from the equation before, if you can see here, the CE the electrical double layer capacitor is equal to the reciprocal of K2. K2 is the capacitance obtained from the tilted spike here, and it's also equivalent to the E0 A divided by lambda. So we can get the value of lambda is equal to K2 E0 A. So by using this one, we can substitute into the equation D is equal to lambda squared per tau 2, and since lambda is equal to K2 E0 A, so we can get the new equation for diffusion is equal to K2 E0 A squared divided by tau 2. And based on the Nernst-Einstein equation, the mobility is equal to ED divided by KT, and we can have a mobility value, equation of mobility as this one. Okay, and since the conductivity is equal to N mu E and also D divided by RA, we can have a new equation related to the equation obtained from the derivative equation obtained from the from our method just now with the with this equation. Okay, so this is example of using the equation of derived from the what I have mentioned just now with some sample that we obtained in the lab. So we use a methyl cellulose, and we use a salt as a lithium bisoxalatoborate solid polymer electrolyte with a low concentration. So in this work, we use a salt from 5, 7, and 9 weight% of sample. So this is the plot of a Nyquist plot of the MC-Libov solid polymer electrolyte obtained from the experimental. We have a depressed semicircle and a tilted spike. You can see here, there's a tilted spike at this site. Then we fit the equation. Okay, we fit the plot using the equation mentioned before. And if you can see here, the equation or the fitting must fit on the experimental point. So because it must fit according to their corresponding frequency, right? So that if we can fit corresponding to the frequency, so our fitted what we can say, our fitted is true. Okay, it's right. So this is what we can see here. We can see that all the fitted point and fit with the experimental data, and this is the value of the parameter value of the fitted point. Okay, from this, so using the equation derived just now, okay, we can determine the value of we can see that here we need the dielectric constant, but we don't have a dielectric constant. So how to obtain the dielectric constant of material? We need to plot a real part of complex permittivity against frequency, and at a high frequency, and from this plot, the real permittivity against the frequency, we can determine the dielectric constant of material at the high frequency. As mentioned by Prof. Aruf yesterday, to plot a permittivity against frequency, we must plot log permittivity so that we can see that at the high frequency, the dielectric is almost constant. Okay, if you can see here, we take the dielectric constant of each material at log frequency of 6, or we can say at 1 megahertz. All right, so this is the value obtained from the fitted and the value obtained from the dielectric and the corresponding dielectric constant of each sample. And here we can see this is the value of N, mu, and D that we calculate from the fitting method. So we only do a fitting method, so we need some supported data or to validate the calculation that we done, we calculate from the fitting method. So in order to validate the value of N, mu, and D obtained from the fitting method, we perform the FTIR and we deconvolute the FTIR band corresponding to the free ion and contact ions to determine the percentage of the free ion and contact ion. So this is the FTIR and the convoluted peak for MC Libov at low concentration. So based on the reference, the position of the free ion of Libov is at 1802. The position of ion pair is 1812, and ion pair also at 1826. So with the area under the graph, based on the area under the graph, we can calculate the percentage of the free ion. So if you can see, this is the percentage of free ion we obtain from the deconvolution method. And we also can calculate the number density, mobility, and diffusion coefficient using this equation. And this is the value of the mu and D obtained from the FTIR method. Then what we do is we compare the value of diffusion coefficient, mobility, and number density obtained from FTIR method and fitting method. And we can see that the value obtained from fitting method and FTIR method is close each other, which is not too far. The difference is not too far, and it is still in the same magnitude order. So this indicates that the method and the calculated transport properties of charge carrier calculated from the fitting method is, we can say that is valid to use in the polymer electrolyte. And if you can see here, the conductivity of this is a plot of, we want to see what is the relationship between conductivity, number density, mobility, and diffusion. So if as I mentioned just now, conductivity is directly proportional to the number density of charge carrier, mobility, and elementary electron. So if you can see here, when we increase the Libov concentration, the conductivity, the top one, okay, here, this part, increase. So why the conductivity increase? This is a method, or this is a way to explain why the conductivity is increased. We can see that the number density of charge carrier, when we increase the Libov SOP, the number density of charge carrier increase. And the diffusion and mobility also, we can see that is almost constant. So we can conclude that the conductivity trend in the sample, in the electrolyte system, which is the MC-Libop system, is dominantly contributed by the number density of charge carrier. So when we add a number of many Libop, for example, many salt, so the salt will LiBOB will dissociate, become Li plus, BOB minus. So when we have more LiBOB, Libop, salt, so more Li plus, more BOB minus. So that's why we can see number density of charge carrier is increased. But the mobility is almost constant, meaning to say that when we add more salt, they are not excited, means that they flow with the same diffusion. They flow with this, they drift with the same velocity. So we can say that the increase in conductivity may due to the number density is dominantly influenced by the number density of charge carrier. All right. So we also try for the other system. We use polyacrylonitrate and Libop lithium-based oxalate solid polymer electrolyte, which is this one as at high salt concentration, because we want to see what has happened at the high salt concentration. This is the Nyquist plot of PN Libop solid polymer electrolyte obtained from the experimental experiment. So we can see that the semicircle and tilted spike at the lower frequency range. And this is the fitting. This is the plot of the Nyquist plot with the corresponding fitted point. We can see that the point is almost fit with the experimental data, and this is the parameter used to fit the Nyquist plot obtained from the experiment. Okay, and since to calculate the N, mu, and D, we need the dielectric constant. So we need to plot a graph, real permittivity against log frequency. We can see that this is almost constant at a high frequency. At this point, we use at 100,000 hertz. The frequency, the dielectric constant was taken at 100,000 hertz, and we can and this is the value of the dielectric constant of each sample. We can see then in order to validate the value of N, mu, and D, we perform the FTIR deconvolution to calculate the number density of charge carrier, to calculate the percentage of free ion and ion pair, and compare the value of N, mu, and D obtained from the FTIR deconvolution with the fitted point. So this is the FTIR deconvolution of PN Libop solid polymer electrolyte. Similar, the free ion position is at 1802, quantum ion is at 1812 and 1826. And the same equation we use, and this is the value of the N, mu, and D obtained from the FTIR method. Okay, and again, we can see that the value or the value of the N, mu, and D obtained from the FTIR and impedance and fitting method is close each other, and the trend also follow the trend obtained from the fitting method follow the same trend as FTIR method. So, and we can see that it is also in the same magnitude order. So this again strengthen our method, so that the fitting method is valid to determine the N, mu, and D in polymer electrolyte. And this is the summary of the plot of sigma of conductivity N, mu, and D. We want to see what can we relate. We can see that the conductivity, this is on the top one, increase when we add more Libop salt. Okay, we can see that the increase of salt from 10 to 50 increase, gradually increase, and we can see that the number density of charge carrier also increase, and the number and mobility of charge carrier also increase. So in this system, electrolyte system, which is a PN Libop electrolyte system, the increase in conductivity was governed by both, meaning to say that the number density of charge carrier and mobility both play the important role to increase the conductivity of the electrolyte. Okay, all right. Then again, we use this. That one is a result at the room temperature. We want to validate. We want to test. We want to see whether this equation can be applied at a various temperature range. So we use the one sample, which is a 91 weight% of methyl cellulose and 9 weight% of lithium bisphenol borate, solid polymer electrolyte. We perform the impedance measurement from 30 degrees Celsius to 100 degrees Celsius. Okay, and we calculate the N, mu, and D. So this is the results of N, mu, and D obtained from the FTIR and fitting method. So we also perform the FTIR at various temperature, and we deconvolute and we calculate what is the value of N, mu, and D. And we can see that the trend obtained, the trend from both method is the same, and the value of N, mu, and D is not too far. It's close each other, meaning to say that the method obtained, the method from the fitting method is, the value obtained from fitting method is close to the FTIR method. So this indicates that the method that we just what we call shown is valid to determine the N, mu, and D in the electrolyte. And we can see here the conductivity of the electrolyte. When we increase the temperature, the conductivity of electrolyte increase. Okay, and the increase in conductivity with temperature is due to the increase in number density of charge carrier. And we can see that the number of the mobility and diffusion coefficient is actually, it's not they are not increased too much. So this indicate that when we apply temperature, so the ion means that the salt have more energy. They absorb energy from the heat, and they can break, become more free ion. So this is proof. So we can see that the number density of charge carrier increase when we increase temperature. So when the ion have when the salt have enough and absorb more energy, so it will vibrate at a high amplitude. So it will break the lattice energy, become free ion. So more heat we apply to the sample, so more energy absorbed, or more energy absorbed by the salt, and it will form more free ion. So we can see here it increased, but the mobility is not increased too much. So this is maybe because of when more salt in the polymer, more free ion in the electrolyte system, so the diffusion, they may collide each other. So they cannot, maybe the mobility decrease because it's not increased too much because they collide which more they collide frequently in the system, so that the mobility cannot increase so much in the electrolyte system when we increase the temperature. Okay, so we can conclude that we have developed the necessary equation to calculate the number density, mobility, and diffusion coefficient of mobile ion from the impedance spectroscopy. And the fitting of Nyquist's plot method based on the equivalent circuit model was observed to provide close value of the number density, mobility, and diffusion coefficient of charge carrier, which is two FTIR calculation, which is, we can say that is based on the stoichiometry method. All right. So we have published these results in the paper in the physical chemistry, chemical physics in 2014, and you may refer to this paper to understand further about the method. Okay, and if you are interested about the impedance spectroscopy, we also have wrote one book entitled Introductory Impedance Spectroscopy. So this is wrote by Prof. A.K. Aruf, me, myself, and also Professor Emeritus M.A. Karim from Sri Lanka. All right. So this is the content of the book. If you are interested to have this book, so I can post the book to you. So the book is with me. Okay. If you're interested, I can send to you. All right. So from that, I would like to say thank you for your listening, and that's all from me. Thank you.
Thank you very much, Dr. Noor. Really, the talk was so informative. And this is very good, very important for those who are actually working on the polymer electrolytes and they want to work on the impedance spectroscopy. My voice is clear to you?
Yes, yes, clear, Dr. Amit.
Okay. Because as we all knew that if somebody is working on polymer electrolyte, then he has to go with impedance spectroscopy, because without having this characterization, nobody can conclude the conductivity part of their sample. And still, it's a major part, and so many researchers are struggling with the way how to conclude, how to calculate, how to analyze this particular technique. So this is really very good, very informative. I have a few questions from the participant side, and I have a bulk of questions from my side as well. So the first question has been asked from Dr. Sandhya Gupta. Dr. Sandhya, if you are there, you can ask your question. Otherwise, I can narrate your query here. Dr. Sandhya?
Thank you, Amit sir.
Very good morning.
Yeah, my voice is clear.
Yes, yes,
Yeah,
I can
very
hear
clear.
you.
Yeah, good morning. Actually, my question is that if in the practically if the this pole plot is not Nyquist plot is not a start from the origin, means if the semicircle is not a start from the origin, so what should be the correct value of bulk resistance? As per my opinion, if the resistance is very low, means it is below the 10 ohm, so we can consider it will be start from origin. But if the resistance is more than 50 or more than 100, so what should be the correct value of bulk resistance?
All right, thank you, Dr. Sandhya. Okay.
Yeah,
Basically, you say that the cocoa plot is not start from origin, right?
yeah,
So
yeah.
that is because of the frequency range. It's not
Yes,
enough frequency range. All right.
yes,
So
yeah.
maybe if you want to have a point close to the origin, we need the higher frequency. Okay. But
Yes.
sometimes there is a limitation with the instrument. Okay. As mentioned by Prof. Arov yesterday, you can convert the value of impedance to the admittance. From the value of the admittance, the inclined plot, the intersection of the inclined plot with the x-axis, you will have the value of bulk resistance.
Means we have to plot the intersections, then we take the value of this R as a bulk resistance.
Yes, yes.
Okay. Thank you.
All right.
Thank you.
Anyone else? Any other participant? If they have query, they can ask their question directly by keeping their mic on mute. If any other participant has any query. Okay. I have some query, Dr. Noor.
Yes,
The
Dr.
first one is like in most of the studies, you have mentioned that you are using the FTIR deconvolution technique. For this FTIR deconvolution technique, you are using some software, I think.
Yeah.
Or the curve fitting method.
We are using an origin.
You are using directly origin.
Yes.
How we can say that these results are very much close to our, like just having a plotting or like comparing the curves, or just how we can say this data is accurate, how
Okay.
it's reliable.
From the FTR, you mean, Dr. Amit?
Yeah.
All right.
By
Okay.
the FTIR.
Basically, we are fitting the plot so that we try to get a good regression.
Right.
Yeah, if we can get the higher regression, the good regression means that our fitting is close enough. And basically, this is the software, right? A method that we apply. So we have to try more than 3 times. We cannot only try one, then we can take the data. So that's why we need to perform for 3 times. Then we get the average value so that we can have the what we can say, the validate data. Right.
And how you analyze the relation between the dielectric constant and the conductivity? Because most of the time you have shown that the graph between the log of frequency with the log of real part of dielectric. If I'm not going the real imaginary part, if I'm drawing the graph or the dielectric, and how you correlate this the conductivity with the dielectric plot? what is the relation? Like if dielectric is increasing, then the conductivity is increasing, or is there a inverse relation between the dielectric and conductivity?
All right. Okay. Actually, there's also a relationship between the conductivity and dielectric, because the dielectric is the number of, if we have a large number of ion accumulate at the interface, we will have the dielectric value, dielectric constant value, right? So that meaning to say that we have the high dielectric, when we have a high dielectric value, meaning we have a high number of charge carrier, means that we have a number and high number density of charge carrier. So the high number density of charge carrier may give some information with the conductivity. So it may say that the conductivity of our sample also high. But in some cases, we also sometimes observe that the conductivity trend is not follow the dielectric trend. Maybe because of the mobility. Because the conductivity is proportional to number density and mobility. So maybe the number density of charge carrier is higher. So that's why the dielectric constant is higher, but conductivity decreased. Maybe because of the mobility have dominated the system. That's why conductivity is decreased.
That's the reason. Because like nowadays, many of us are following the pattern of finding the concentration of charge carriers and mobility. So I think this N and mu can help us to understand the pattern of dielectric and conductivity, how they are not following each other. We can find. And what I conclude out of your presentation is like N and mu plays a very crucial role. And sometimes this, because of larger number of charge ions, mobility may drops down because of the larger concentration, and the ions are not moving enough space to move from one point to another point. So this is somehow affecting our overall conductivity system, I think.
Yes, that's right.
Yes, very good. So this talk was so informative, at least for me. I think other participants also enjoyed and they learned out of this, because as per my concern, every researcher who is working on polymer electrolyte, the first characterization technique they perform on the sample is impedance spectroscopy. Without having the idea on impedance spectroscopy, they will not move to FTA and XRD, because everybody is interested on the ionic conductivity. If we are able to increase it, then it's worthful for us. Otherwise, there's no sense of adding anything into the polymer, post polymer. And I have gone through with your many other papers also on which you have worked on biopolymers, and there's more emphasis and attracting me on this area, because polymer, the synthetic polymer is absolute in market. Now everybody's trying to get the biopolymer based system.
Yes.
So I will be in touch with you to have the idea on the biopolymer electrolyte system.
All right. Thank you, Dr. Amin.
Thank you. If anybody else have any question, then we can move forward. Otherwise, we can close for today's session. Any other participant? Anyone from Malaysia? A student of Dr. Noor?
Any question from Malaysia and India?
Yes. Any question from Malaysian students?
So this is very nice. Actually, this is a nice talk, actually.
Nice, very good. It's very good. And you have explained in great detail. You explain all the equations and all the terminology in great detail. Somebody is writing that Ikhwan, thanks for your interesting talk. Really, a talk was so interesting. And yeah. So I think it's time to close our session. Thank you very much, Dr. Noor. And we'll meet tomorrow at 11:30 once again to get the information on solar cells. Our tomorrow's speaker is Professor Bhaskar Bhattacharya. And he gave his insight. He put light on the solar cells and their functionality and challenges and all everything. And that information will be, the talk will be a good. And I request all the participants to join till 11:20. We start sharply by 11:30, right? And I will take your attendance directly from Zoom. No need to fill any Google form today. Yesterday I got some technical issue. That's why I spread out the Google form. But today I will get it from the Zoom directly. So thank you very much. Thank you all for joining us. Thanks a lot, Dr. Noor, for spending your time and for a valuable talk with us. Thank you. Thank you very much.
Thank you, Dr. Hamid and all. All right. See you tomorrow.
Okay. See you tomorrow. So I'm closing the meeting for today.